Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
My experimental discovery of practical parallel supercomputing that occurred on the 4th of July 1989 of how to reduce the supercomputer time to solution of grand challenge problems and reduce it from 180 years to just one day, in effect distinguished between what's computable and what's not computable. Climate models must be used to accurately foresee otherwise unforeseeable long-term climate changes. In theory, extreme-scale high-resolution climate models are computable, but in practice, a climate modeler may need to run more than 1,000 accurate simulations. If each accurate simulation of the planet's climate has a time to solution of 180 years, then the climate modeler that began her simulation 2 millennia ago, or in the year Jesus Christ was born, will complete her forecast in nearly 2,200 millennia from now. I was the first computational physicist to experimentally discover how to parallel process across an internet. I was in the news headlines because I discovered how to parallel process extreme-scaled computational fluid dynamics codes and how to simultaneously execute them in parallel and how to synchronously email them across a new internet. I was the first person to experimentally discover how to reduce 180 years of time to solution of a grand challenge problem being solved on one computer to just one day of time to solution across a new internet that is de facto one supercomputer. That new internet is a new global network of 65,536 identical central processing units that I visualized as equal distances apart from each other and on the surface of a globe that I mathematically visualized as embedded within a 16-dimensional hyperspace. Along my way to that terra incognita called parallel supercomputing that was then an unknown and unexplored territory that had no map, I employed a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of calculus that encoded a set of laws of physics, including the second law of motion. I used those partial differential equations to formulate 65,536 initial boundary value grand challenge problems. I discretized those grand challenge problems of calculus to obtain a set of linear equations of extreme scale algebra. I reduced calculus to algebra because algebra is the only way the supercomputer can experience the laws of physics. Those linear equations were at the algebraic core of my extreme scale computational fluid dynamics codes. I executed my 65,536 codes in parallel and across as many tightly coupled processors. In a manner of speaking, I use those 65,536 processors to poke my nose into the laws of physics and to discover how the millions upon millions of processors that powers the modern supercomputer can be harnessed and used to foresee the otherwise unforeseeable climatic changes. I discovered that I can use those 64 binary thousand processors that outline and define my new internet, and that I can use them as one cohesive supercomputer that can execute an extreme scaled high resolution global circulation model. Parallel supercomputing is a precondition to foreseeing global warming. My contribution to the development of the computer is this: I redefined the boundary of what the computer can compute, and I redefined that boundary by a factor of 65,536.
Insightful and brilliant lecture.